So a rope is pulling in a boat with a constant force of 200 pounds in the direction of motion of the boat. So as the boat is moving horizontally, the rope is also moving horizontally. How much work is done if the boat is if the boat to shore is 500 feet? I'm trying to pull the boat into shore. So this is a simplistic problem, and it uses the work equals force times distance formula. So you set it up rather easy. Work equals force times distance. And you plug in the numbers. It's a very simple formula. So work in this case, as long as the force and the distance are going in the same direction, unlike our little radio flyer card up here, where the force of the object is actually at an angle and the direction of the motion is horizontal. So this becomes the simplistic case, though the world doesn't work very well in the simplistic case most of the time. So where do I get force from? What's a force measurement here?
The 200.
The 200. Because pounds is a force, it's caused by gravity. If you went to the moon, you would weigh 1/6 of that force. Because that has nothing to do with mass. Mass is totally different. So the force is 200 pounds, so I'm going to put in here literally all of it, 200 pounds. Because the unit of measure is really important for this type of problem. Because it's really strange. The distance that we're going to travel is 500 feet. And simplistically, multiply them together. What was that, 10,000?
Mm-hmm.
No. 4, 5. That's 100,000.
Yep.
100,000. So this turns into what's called 100,000 foot-pounds. Literally, foot-pounds is the product of feet and pounds. It's a very strange measurement. There's a better one in physics. It's called a Newton. It's much easier to work with. But for English measurements of feet and pounds, you get the foot-pound. All right, so that's simplistic. So what we have to talk about is what happens if our vectors of the direction of motion and the force are going in opposite direction. So for instance, let's just talk about just vectors for a little bit. Let's call this vector v. Let's call this one vector w. And let's imagine that vector v is the force vector, and vector w is the direction that I'm going in, and the distance vector. Just imagine for chance. So if I could get the radio cart's force to go in line with the direction of its motion, then I could just do the problem as force times distance. Does that make sense?
Mm-hmm.
All right. The problem is, how do I bring the force down so it applies properly? So if you're pulling up at an angle and I change it to lying down, do I have to keep the force the same?
Yeah.
It'll be easier, right?
Mm-hmm.
To pull it straight rather than at an angle and have it drag across the ground. So when I bring this force down, it's actually going to be, well, in vector terms, shorter, or a smaller force. And it's directly shorter as an altitude off of the end of the arrow. And the vector we're going to be looking at is this vector here. So this is what's called the projection of the vector v. That's great, except for it needs one more little label. And the little label is, what vector is it being projected onto? And it's being projected onto w, so you get a little w down there. So it's called the projection of v onto w. I'll write that in English. Projection of vector v onto vector w. That's what this notation means. Projection. And the way I think about it is, imagine that the sun is directly above this red dotted line, and it's shining down on vector w. Then vector v is going to create a shadow exactly as the projection here. Does that kind of make sense?
Mm-hmm.
That if the sun was there and it was beaming like this way, you would have the shadow along w that is the shadow of v. They just call it a projection. So what we need to do is come up with a formula or a way to find this projection of v. So one thing you have to know is what is this angle. Now, if I know what V and W are componently, we can always find the angle. That's easy. If V and W are component, this formula is going to ignore the angle eventually, so that's kind of nice also. So I'm looking for a right triangle here. So if I have this right triangle, I'll draw it separately. What works on a right triangle is trigonometry, but trigonometry can't work with vectors. So what do I have to have on the sides? When you have a right triangle set up, what do you have on the sides when I label them? What are they called? Like 3, 4, 5. What are those numbers called? What do they represent?
Lengths.
Lengths. So what would be the length of vector V?
Vector V.
Vector V is like A comma B. That's not a length. So what is its length?
V.
What's the length of the vector called?
Magnitude.
Magnitude. Oh, so the hypotenuse becomes the magnitude of V. And what we're looking for down here kind of is the magnitude of that side. So I'm just going to call it X. We're going to let that represent the magnitude of the projection. I just don't want to write out PROJ, VW, and all that fun stuff. So this X represents the projection, that thing, magnitude of the projection. And we have this angle theta here. So what trig can I apply to this right triangle? No. I don't need to go into law of sines and law of cosines. This is simple trig. It's a right triangle trigonometry. Cosine? So you go cosine of theta is equal to adjacent over hypotenuse, so x over the magnitude of v. I used to you being late. And then what I'm interested in is the length of the bottom side here. So x is equal to the magnitude of v cosine of theta. That's the magnitude of that side. Great. But that doesn't tell me what the vector is. It only tells me the magnitude. It doesn't tell me the direction. So what I'm interested in now is, sure, I know what the magnitude of the projection is. I just don't know its direction. Well, what direction is it going in?
Outward.
Well, it's the same direction as W. So this becomes the magnitude. And all I need is the direction of W. And I want to write a vector that has that magnitude in the direction of W. So, do I just take this magnitude and multiply it by W? You know, scalar multiply? Make it that magnitude bigger? Would that work?
No.
Why?
No.
Well, if W was 5 units long and this magnitude was 6, you'd get 5 times 6, which is 30. But I really only want 6. So what do I have to change my W into? Something that when I multiply it by this magnitude of 6 from the projection, that it stays 6. So 6 times what leaves it as 6? 1. So what I need is a unit vector of W. So while we're going in the direction of W, we need a unit vector. Remember how they're notated? It would be W caret hat. I call it hat. So we need the unit vector of W hat. Great. How do you find the unit vector of W hat? It's like a review of all of the vector crap that we've done. So, W hat is equal to did I forget to ask this for a homework problem?
We didn't give us homework yesterday.
Oh!
Yep.
Dang it, that's why. My fault. You should have done checkpoints at least.
Oh crap. I
Oh
didn't do
crap,
this.
yeah, those checkpoints. Alright, to find a unit vector, you take the vector and you divide by its magnitude. Because when you find its magnitude, then you get the magnitude divided by the same magnitude, which comes out to be 1. So this is equal to the vector W divided by the magnitude of W.
But none of the homework yesterday was on the review, so does that mean it's not gonna be on the test?
Oh, well, some of it is the sum and scalar products of
There was
vectors.
that dot stuff.
There's a dot product with the projection. That's one problem that covers magnitude, dot product, and the angle in between two vectors. So it has all the pieces there. It's just I shove them into one problem.
Okay.
I don't ask it individually because that's quite boring. Jeez. All right, so here we have the magnitude. That magnitude of v cosine theta is the magnitude of that red vector. Here we have the direction I want to go in. The magnitude of w, the vector w divided by the magnitude of itself. So if I take these two and multiply them together, I have its magnitude and I have its direction. All right, last little piece then. Therefore, the projection of v onto w is equal to the magnitude, which is, I'm going to have to rewrite this over on the other side of the board, of w cosine of, that's supposed to be a v, magnitude of v cosine of theta, that's its magnitude, times, this is not a dot product. Why is it multiplication? What is this thing? A scalar, a number, nothing to do with a vector. All right, it's going to be times this vector w divided by the magnitude of that vector. Okay. So this is a decent formula for the projection of v onto w, except for one problem. It has cosine of theta in it. That means you, if you're not given theta initially, you have to actually go and solve for it. I doubt they have that formula in the book. There. All right, so let's add a few things. A few things you should know. V dot W, well actually, cross that out. If V is equal to AB, and W is equal to CD, then V dot W, just for review purposes, is equal to what?
AC plus BD.
AC plus BD. If you line your vectors up the way I have written them, then it makes it really easy to come up with the dot product because you just look vertically. If you put them next to each other, you have to remember first times first and second times second. So if you're working with vectors, it's actually better to stack them. All right, the other thing I need you to remember is there is an alternate definition for V dot W. What is it? It's in yesterday's notes. Do you want me to just give it to you?
W dot V.
Oh, well, yeah, that's the commutative property, but I mean another definition of how to find the dot product besides multiplying their components and adding them together.
Is that the cosine?
W. Wait.
It's got that cosine in
Magnitude of W. What?
Magnitude of
I
V,
can't read my handwriting.
I know, times the magnitude of W,
Cosine theta.
cosine of theta.
That's the only thing I can make out.
That's the other one. Now, from this formula, you can rewrite this as cosine of theta is equal to V dot W divided by the magnitude of V, magnitude of W. Just dividing the magnitudes across. That's just an alternate form. And that's how we solve for theta. We did that yesterday, solve for theta. You know,
We did it.
cosine, it was the last one we did.
Yeah.
Or second to last one we did. All right. So now, we have two things to put together. I have this projection written this way with an angle in it. I don't want the angle in it. I have this cosine of theta equal to things in terms of vectors, dot products, and magnitudes. So what I'm going to do is I'm going to get rid of this cosine of theta here and replace it with that mess. It comes out rather nice after we're all done. So putting the two together, this and I'll have to write it again over here. Projection onto W of V so far is equal to the magnitude of V cosine of theta times the vector W divided by its magnitude. That's what we have so far. And what we're going to do is take this and just plug it in here. That's all I'm going to do. One little step. So taking these two things and putting them together, we get this. I'm going to reorganize a few things. Number one, I'm going to reorganize. Take this magnitude of W and shift it way over here towards the magnitude of V. Is that legal?
Yeah.
Why?
Just still multiply.
It's all multiplication, and multiplication is
Commutative.
commutative. The second thing I'm going to do is the denominator of cosine of theta, which is magnitude of V and magnitude of W, I'm also going to shift it under the magnitude of V. So, what we get is V dot W divided by, now remember the cosine is gone, the V dot W is replacing it, the magnitude of V, magnitude of W is going below the first one, and that magnitude of W all the way from the right is also coming over. So how many magnitudes of W am I going to have?
Square.
Squared, two of them. So this will be magnitude of V, magnitude of W, squared, I think I screwed up some place. Hold on. W magnitude of W, V dot W,
You just need the last vector, the W vector.
the W vector, but there's still something messy here.
That's why you have
That
on
would
this
be
paper.
cosine M. Wait, no.
Hold on. Brain fart. Oh. We get the magnitude of W squared, but we also get the magnitude of V squared, don't we?
No. When the V cancel out.
Yeah, there's one on top. There's one on top, that's right. There we go, thank you. There's still one on top. And then this is times the vector W. Phew, thank you. Missing a piece.
Wait,
All right,
where'd the regular V?
hold on. The V dot W comes from here. All right. The magnitude V magnitude of W comes from here. The second one for the W comes from here. The second one, or the top one from the V comes from there. And then these two are going to cancel rather nicely. There, now it looks perfect. So we get the projection of W onto W of V is equal to V dot W divided by the magnitude of W squared times the vector W. And that's our formula. I think it was like pulling teeth. Bet there's an easier way to do this, but oh, it always comes out, no matter which way you do it. What's nice about this formula compared to the original one with cosine in it, if you know what theta is, this one actually works out better. This first formula we came up with. But most of the time you don't know what theta is, and it's actually easier to work this. Here all you have to do is a dot product, a magnitude, and the whole first part, you gotta be careful of this. This whole first part right here, this is your scalar. The vector is here. And the answer of a scalar and a vector, of course, is a vector. And you have to keep track of what's a scalar and what's a vector when you're working with vectors. Otherwise, you can get really, really confused.
So with that one that's cosine equal, you're gonna have to do all that and cosine inverse of it.
What are you talking about?
If we're trying to find the angle.
Oh, if we're trying to find the angle, yeah, you do cosine inverse of this whole ugly mess. And it's not pretty, and these usually turn out to be two square roots. It's better to write it as a square root of this times that, than two
But we
square
won't-
roots.
Will we have to just find,
I'll ask you to find an angle, yeah.
like, with using that formula?
Yeah, using the cosine theta formula. All right, so what is the point of all this?
Are you gonna give these things the formulas on
I'll
the
give them
test?
to you, especially that one. That one gets confusing because I always get confused where the W is, the bottom one. The W happens the most often,
Mm-hmm.
and V only happens once.
So what will we need to memorize?
You don't memorize that. I'll give it to you.
But I'm talking about for the other sections. Alright, we don't need anything for the other sections, just so
What do you mean? Like laws of
yeah, like
identities and things like that?
No, that long law of
Like any other
cosine.
formula.
It's not long, but
You better know the law of cosine and the law of sines. Those two you memorize.
alright.
C squared equals a squared plus b squared minus 2ac. I mean, it's not that hard.
I know, but I'll just ask.
So, for example, if you have our little cart, there's lots of stones in it, whatever, and you have the handle up at an angle like this, and you're moving in the direction that way, and we know this angle is theta. So for this problem, let's let theta equal 60 degrees. Crazy angle. Let's let the distance that we're going to be traveling 20 feet. And this one's going to be called F now. This is my force vector, so we'll call it F. And the magnitude of my force vector, let's say, is 50 pounds. Okay, ready? If there's 100 pounds of rocks in this wheelbarrow, or whatever the heck it is, my red flyer, and I apply 50 pounds of pressure to the post at a 60-degree angle, is the cart going to move?
No.
Damn it. I don't think it
Because
would,
it's harder.
because
If
first
you-
off, you're
only way
losing
it
a
would-
lot of power going at an angle.
The only way it would move if it was tilted further down.
Well, I don't know.
Like if you made it a negative 60 degrees.
If this weighs 100 pounds and you're pulling with 50 pounds of force,
I'm saying,
I'm
what
not
if-
seeing it.
well, okay,
Maybe it won't move that much, but it probably would move. I have to play.
Yeah.
Because a little kid pulling on your arm could actually pull you down, but they weigh less than you do. So I guess it's possible. I'm not a very good physics person.
I was just saying, like,
but it wouldn't
in a
move very
concept,
fast.
yeah.
That's for sure. All right, but it's pulling with 50 pounds of force off the direction of motion. So it's really not pulling with 50 pounds. It's pulling with something a little bit smaller. So what we want to do is we want to come up with a way of figuring out what the work is done as it travels over the 20 feet. So we set it up like this. Do a little coordinate system.
wait,
What?
so are you saying that the rocks are 100 pounds or
Eh,
they're
well,
not?
it doesn't really matter.
It doesn't matter.
It doesn't really matter. You're applying force to it. It should move.
I thought you said it wouldn't move.
I wasn't thinking it would, but it's on wheels.
But if you're pulling, but that's pulling up though.
It doesn't matter. You're applying force to something, it's going to move. If you're in space and you give a little force to something, it's going to move. So you're assuming it's a frictionless surface that you're pulling it across. Now, if the rocks were on the ground and you have to deal with friction, it ain't going to move. But I think with the wheels it would. So you set it up as, here's your force vector. The angle here is 60 degrees. And you want to move this cart 20 feet. And the cool thing is, you can change the motion of this object into a vector. One becomes a force vector, the other one is called a distance vector. So we want to move this thing 20 feet. So this, I would call this the D vector. I don't know, it's a good name for it, D vector. What would be the formula or the components of D vector? What would be the components or the parts that make up the D vector? Remember yesterday we had that weight, you weigh 200 pounds, your vector is negative 200j, because you're going straight down, or 0, negative 200. What would be the vectors of D if D is 20 feet?
20 out.
20 comma,
Zero.
well 20i plus, well nothing, yeah. Or, I like components, so 20 0.
So
That's a perfectly
there
fair.
is no I?
Or 20i plus 0j.
Okay.
It's the same thing. I just like writing it this way because I can't stand writing I and j because people do weird things with them, like I squared, j squared, which is not what you're supposed to do. All right, so what I need is, for work, I could care less about what the projection is itself. The projection by itself is kind of cool, but for work purposes, it's not necessary. All I need is the magnitude of this vector, that length. So how do I find that length? Remember, if we call this x, this side is the magnitude of f.
D minus.
Cosine, or
Yeah, cosine. It would be x equals the magnitude of f cosine of theta, right? That'd be the easy way of doing it. All right. So if you want work is equal to force, not an arrow, force times distance, the old-fashioned force times distance, this would become work equals force, which is this thing here, times distance. Well, distance in terms of vectors would be what? I know it's 20, but how would you represent it with a d instead? The distance is 20, I know that. And the vector is 20 comma 0. But how do I find the distance of the vector? What's that called? We talked about this earlier. The distance of a vector. The length of the vector.
Magnitude.
The magnitude of the vector. So this would become the magnitude of f cosine of theta times the magnitude of the distance vector. Or we could rewrite it as the magnitude of f times the magnitude of d cosine of theta. And you get this neat little work formula. That has nothing to do with the projection, though it has part of the projection in it.
Doesn't matter how you arrange that.
No, but it's better to have the magnitudes first and then cosine of the angle last. Alright. So with this problem, the way it would set up is this. You would have work equals the magnitude of f, magnitude of d, cosine of theta, and you plug in your information. So the work equals, what's the magnitude of f? How many pounds am I pulling this cart with?
50.
50, so that becomes 50 pounds. The magnitude of d is what?
20.
20 feet, so this would be 20 feet. And then you multiply it by the cosine of theta, which is the cosine of 60 degrees. Now what that cosine of 60 degrees does, if this was pulling straight, it would just be 50 times 20. The cosine of 60 is going to be less than 1. Cosines always have to be less than 1. So what that does is it reduces how much work is actually being done because the force is actually being reduced by that factor. Cosine of 60 is a half.
Mhm.
So this would be, the work is equal to 500 foot-pounds. And that's all there is to it. Ta-da! Now that's all the book talks about.
You did all that in your head.
What, half of 20 is 10, 10 times 50 is 500. Cosine of 60 is a half. Cosine of 60 is a half. So, yeah, I'm going to make a problem look like that. There is another flavor to this. To the work equals force times distance. And it's actually a nice flavor, I think. Then we can do some problems out of the book, if you have any good ones. Well, good time. So let's see if I can figure this out.
Oh.
Just in case you're going into physics.
Which is me.
Okay. For you, the description of another work.
We can talk about that when I get to physics, though.
No, because they don't derive it for you. They say, here's a formula. Good luck.
Will we have to use this on the test?
This formula here?
Yes.
Yes. We have to use the other one? You don't have to, but it makes life easier in case of one thing.
What other
This formula works great if you know what the angle is.
one?
If you don't know what the angle is and you only have the two vectors, this formula sucks.
So then you have to use that other long one.
Oh, no. This one's much better than that. But we apply the long one to this.
So have we used an example of the long one yet?
No. Oh, that projection one?
Yeah.
Don't worry about that too much. You just plug numbers into a formula and it pops out. It's not hard. I'll do one though. What we can do to get rid of this cosine of theta is go back to its pure definition, which is the dot product on the top and the magnitudes on the bottom. the cosine of theta is equal to v dot w over magnitude of v times magnitude of w.
Can the cosine
Why are you
of
looking at me
theta,
like that? It's just
Because-
the formula.
can it equal x?
Tomorrow is the
Over-
test.
No, x doesn't mean anything to us
Oh,
though.
it doesn't?
No. So this would be f dot d divided by the magnitude of the force times the magnitude of the distance, which is basically just the distance. And if I do this substitution where I shove it inside of that cosine, we get work is equal to the magnitude of f times the magnitude of d times f dot d over the magnitude of f times the magnitude of d. It's a nice substitution, right? Why is it a nice substitution?
Cancel out.
Tons of it cancels out, and you get work is equal to
F times d.
the force vector dotted with the distance vector. This formula is much nicer. If you're given f and d as components, then this makes sense, that the work that comes out of it. And if you get into physics, this is what you use. You don't use the cosine thing, because they give you